Greetings, this is Graham Warren working with you on an ANyLogic simulation model for the Antico Cafe Greco case. So ANyLogic is commercial simulation software. I'm working with a free version here called the Personal Learning Edition. Runs on Linux, Windows, primary Windows, but it has Mac support and Linux support in sort of decreasing levels of completeness. And there's also a cloud version, but the Mac version works just fine, for these kinds of simple models that we're going to consider. So ANyLogic offers three kinds of modeling: discrete event, which is primarily what we have here, and then agent-based, and then system dynamics. So for business process type work, innovation type work, for the most part, you're going to be able to get done with discrete event models, maybe with some agent overlays. So here, this may be the first look that you have of an ANyLogic model, but I'd like to go through some of the basics. The intention here is to provide you with a model, not to ask you to build a model, because the learning curve is a little steep. We will offer, a workshop to get you situated and get you started with modeling. But, the intention is not to model. It's basically to consider a business process and then to think about innovations through the lens of, the various lenses that we're going to address. So what are we seeing here? This is the main canvas of the model, and here is the essential model. So this is a drag and drop kind of setup. And what you have here is a palette, and there are various palettes for various kinds of models and features of the tool. And I'm using essentially the process modeling library here. Typically going to be using this for business process type modeling. So we have what we call a source block here, which is going to be used to generate customers or flow entities in our model. And the base case of the simulation has here an arrival rate of 18. But I'm going to specify this as a parameter of the model. So we will have these models are sort of versatile in the sense that we could change parameters like the arrival rate, the mean service time, and so forth, and simulate, in a somewhat analogous fashion to the way we use queuing analysis to explore various scenarios. We can use the simulation tool to mimic some of that. Now, there's just one, concern about getting the queuing and the simulation models to line up exactly, and I'll point that out when we get there. But for now, the arrival process is reliably modeled using this rate function. When I use a rate, I could choose an arrival time distribution, so inter-arrival time. But when I use rate, then the assumption is that my arrival process is Poisson. That's just a built-in assumption of the ANyLogic software. The free tool comes with a maximum number of 50,000 flow units. So I might want to make sure that we don't max out there. So I delimit the maximum number of arrivals. And this information here connects to the animation. I'll get there later. So we've got an arrival process now of 18, well, of arrival rate per hour, whatever it may be. And we're going to start a stopwatch. And then we're going to grab one of the two types of machines. So these are resource pools. And in these resource pools, we have either Victoria Venus Arduinos or Jura machines. These are the options for the ACG coffee shop. And you have to determine if a mixture of machines is possible. The case owner will be providing guidelines on that. It's possible that you may only be allowed to use Venus Arduinos or only Juras, possibly a blend, but that's up to the case owner. So whatever the case, a customer comes in and then looks to grab either a Venus Arduino or a Jura machine. Of course, there's a barista powering this experience. You can see we've got alternative resource sets. We're going to grab one of the two, and if there was just one available, then it's easy. And if there's one of each available, then not quite sure how ties is split, but there must be some logic, maybe just a coin flip or something on that. So got a barista, got a customer, got a machine. Now we make the coffee. And this is where it gets a little interesting. We have a sort of an if statement. This is Java here. And so we check if we've got a Venus Arduino attached to this customer coming through. And if we do have that type of machine involved, then we're going to insist that our service time is normal. Let's just change the color on that again. Put it in red. So we've got a normal distribution here. You can see here is the specification that it's normal. And then I've got a mean service time, whatever that is. And that's typically going to be 103 seconds, right? So that's the mean. And then the base case, my standard deviation is 60 seconds, right? And you'll notice that there's two additional parameters here. And what this does is, since I can't tolerate negative service times, I'm going to truncate it at 0. On the upside, you can go all the way up to infinity. But on the lower side, 0 kicks in here. Now, I think you can see that, there's a bit of probability down the bottom here, because if I take mu minus 3 sigma, then it's 103 minus 180, and that's minus 77. So I'm chopping off more than 1 sigma. So this is not even 2 sigma down here. And so there is meaningful probability sitting down here. So what's going to happen, what the tool is going to do is it's going to continue to sample, but it throws away all the negative numbers. So whenever it gets a negative number by sampling from this distribution, it tosses it and it resamples. So in fact, what happens is the mean and the standard deviation, well, the mean is higher than 103 because of this discarding effect, because I'm truncating it here by 0. There's no real way around it. It's just an unfortunate consequence of the fact that the standard deviation in this particular case is so high relative to the mean. But we do need to truncate. So I just want to mention that. Now, what happens if it's a Jura? Well, I think you can see where this is headed. We're simply going to just switch out the standard deviation. So this is the one for the Venus Arduino. And if that's not the case, then it's a normal distribution, similarly truncated, with the same mean service time, 103 seconds, but now the lower standard deviation of, I think, 5 seconds. Okay, and you've got to specify what those are as parameters. Okay, so that lays out, the coffee making process. Then we're going to release the server, basically the machine, stop our stopwatch, and then the sync is where good customers are disposed of. We're done with that. Now we can collect some statistics, as this simulation unfolds, and that's shown here. So I'm going to be interested in the queue length here, how many customers are waiting to get a machine, what is the utilization of the Venus Arduinos and the Juris machines, and then also using this timer setup. Let's click on this block to show you how that looks. It relies on when I click the stopwatch at the end, this time measure and the distribution. And this time measure end is connected to time measure start, and it's collecting this data the time in the system. So we're able to, to understand what's going on there. Also collecting time in the system here, which is this one here, rather. It's going to report, it just collects data. Shouldn't have made too big a deal out of it. It's just collecting data. All right, and there's a bit of an animation going on here. So I'd like to show you, how to run this, and then we'll just do one run here in the base case, and then I'll have a second clip which will elaborate some of the possible scenarios that you could get into. The purpose of the analytics here is to sort of give you hard evidence to understand, if you do make process innovations, whether they're relevant or not, what kind of value they're going to bring, what kind of deltas they bring. I think there's still a question, as to whether they're going to be a fit for a coffee shop, because there's rich context there. But at least you'd have a sense of, if we did this, then this would be the impact on utilization and waiting times and so forth. So because of those truncated normal distributions in the make coffee block, the match is not going to be perfect. And in fact, the queuing results will be the most exact here. The simulation model and the queuing model in this case are, if I had long simulation runs, they should produce relatively similar results, except for that truncation problem. So to run this tool, you're going to go back to your project block here, your projects. Now notice you will have where is it? Got the main, and here's simulation main. Okay, so when I go here, just moving my zoom windows around, if I expand this, you'll see I can plug in my parameters here. Let's try that again. Parameters preview. I'm just trying to expand this enough. There it is. Okay, so you can see I can plug my actual values in here. And so without having to change blocks in the simulation, this is just convenient. And when you run the simulation, you'll see them appear here. So I just want to confirm that this is in fact the base case. So the mean service time in seconds. You can see I'm presenting it in seconds here is 103. The arrival rate is 18 per hour. The standard deviation of the service time of the Venus Arduinos is 60 seconds for untrained baristas. That is our base case. And I'm just going to be examining one barista, because each of the three baristas in the base case are identical, as explained in the queuing narrative. So to run this model, you can see a little green arrow up here. You may have to pick the model, but I can see it's running the correct one. If I've got multiple models, as I have here, it may be running whatever model you ran previously, which is fine. But you're obviously needing to pivot to get the ACG output. So you can see the parameterization here, and it's running. You can see that 5 customers have come in. I started the stopwatch on them, and they grabbed a server. The one number on the left is how many have entered the block, how many are completed. So you can see there's a customer that came in and got service and then finally got released. So 12 customers roughly have made their way through the system, and we are recording their time in system. Now you can see worst case I'm up to about 3.5 minutes, even though on average we're looking at 209 according to this. So I'm going to speed it up, and we have some controls here. This just speeds it up, 5x, 10x, 25x. And you can see now I'm up to 40, 50 customers, and my distribution is starting to materialize. We can go faster than that yet, up to 50, 100, 250, 500, and 1,000. And now I've done something like 1,000, 300, 400 customers, and you can see I have a right tail distribution. Excuse me, on the waiting time in system. What's a little bit worrying here is that some folks are waiting 10 minutes. You may be satisfied with this, but pay attention to this. We don't get this distributional output from the queuing model, but we can see it here. So what's going on with the queue length? Well, there's not a lot of folks waiting to get service here, only less than a half a customer in line on average. And then the utilization is 53% estimated here. Don't quite know why. There's just a different number of data. The size of the sample going into these estimates, the 54 and the 53, just are because of different sample lengths. There's no utilization of the jurors because there are no jurors. There's just one Venus Arduino here, so there could be no utilization on the jurors. And there's about a 3-minute turnaround, which is roughly what we got from queuing. I think the number was 2.9 and change. That's in minutes. This is expressed in minutes. So I will talk you through the animation in the next clip, but for now we've got an ANyLogic model in front of us. it mimics the workflow of the coffee shop. We're collecting times that we're interested in, and we're able to estimate utilizations and hence assess the performance using meaningful KPIs of the base case.